Okay, welcome to the first in a sequence of screencasts talking about number theory. In this sequence of screencasts, a number equals anything in the sequence 0, 1, 2, 2, 3, 4, 5, and so on. I'm not going to be entirely rigorous when I'm talking here. There's going to be various things which I'm going to sort of assume and gloss over. I could prove them if I wanted, but it would take us far away from what I want to do, which is to give you an overview of number theory for the purpose of Mathematics Olympiad questions. So I'm just going to pile straight in and talk about prime numbers. Okay, so prime numbers. There are some numbers like 12, which equals 3 times 4, which have factors. Or 14 equals 2 times 3. Or 15 equals 3 times 5. So these numbers are called composite. They've got factors. They can be factorised. Of course, every number n equals n times 1, so you can factorise a number into itself from 1. But if this is the only way to factorise a number, sorry, glitch there. If this is the only way to factor a number n, we say n is prime. So these numbers here are not prime. Again, I'm not being entirely rigorous here. So, for example, 2 is prime. You normally say 1 is not prime. And you'll see why in a minute. So the first few primes are as follows: 2, 3, 5, 7. 9's not prime because it's 3 3's. 11, 13, and so on. It's a nice little sequence of numbers. Quite often you talk about an odd prime, which means a prime strictly greater than 2, because 2 has got some rather peculiar properties in many contexts. It turns out I won't prove it because it's not tricky exactly, but it's more difficult than you might think. Any number, I've got a clock here, any number n may be factorised essentially uniquely. So if you have n, you're going to write it as p1 for one prime number to the, let's say, a1, p2 to the power a2, pn to the power an. I won't prove that. It's called the fundamental theorem of arithmetic. So, for example, if I say 210, n equals 210, well, that equals 2 times 105, which is equal to 2 times 5 times 21. See, I'm factorising it by steps. 2 times 5 times 3 times 7, of course. And you normally write the factors in ascending order, so it's 2 times 3 times 5 times 7. There we go. And there's only one way of doing that. I can rearrange. I can say 3 times 2 times 7 times 5, but that's just the same way. I could take a number like 12, and that equals 3 times 4, or 3 times 2 squared. You'll see I can carry on because 4 is not prime. So I'll write 12 as 2 squared times 3. And of course I can carry on like this. So if I want to say 36, that's 2 squared times 3 squared, and so forth. 91 equals 7 times 13, and so on. If you allow 1 to be a prime number, then you lose the uniqueness, because I can say 91 equals 7 times 13 times 1, or 7 times 13 times 1 squared, and so on. So if you allow 1 to be a prime number, you lose the unique factorisation. Okay, so any number can be factorised, and this is incredibly useful. We'll use this fact over and over and over again. Any number can be factorised, and its factorisation is unique, up to a reordering of your prime factors like that. Okay, so I'm going to stop there.